Yeah, I guess we'll find out. All right, good morning, everyone. Today is Thursday, February 10th, 2022. We are starting Unit 3 today. Hopefully all of you are all caught up with Unit 2 and especially Unit 1 and have finished Part 1 and Part 2 of the exam. I will start grading Part 2 of the exam today. So there's quite a few for me to catch up on of those. But yeah, Part 2 was due yesterday. All right, those of you who have a TI 84 or maybe an Inspires might be true, but I don't think many of you do. Last year, there was quite a few people that had the 84, so that's why this is in there. I thought I'd keep it in there just in case you didn't know this, but rather than use the division button, which I don't, it's further down, there's a fraction button, and you just hit the alpha key, then hit F1 or this button here, and then you have this little pop-up here, and you want to select that first option, hit enter, and when you do, well, it's going to have this little fraction dealing. And then if you notice, there's other options here. I haven't played with these, but I have like a fraction to decimal converter. So this one, you can go decimal to fraction to decimal by choosing option 4 by doing the same routes. So those of you who have TI 84, there it is, kind of neat, super useful. But anyway, let's go. All right, we're going to graph parent trig functions. So we're going to use Desmos today. A lot of it is demonstration. A lot of it's just typing stuff in. It's pretty easy from like a math standpoint in terms of calculations, just because it's a lot of just learning how to type stuff in into Desmos and to see stuff. So you use Desmos or GeoGebra. I don't like GeoGebra for a few reasons. There's limitations I found in GeoGebra later on this. I don't know if it's this unit or next unit, but it doesn't do the math right on certain problems I noticed. It's kind of weird. And maybe they fixed it, but Desmos seems to work fine. Okay. So when we input these functions, it's going to be in terms of radians. So like whenever you graph stuff and you look at it, it's always going to be in radian mode. So whenever you have something in degrees, we will have to most likely convert it into radians always. Almost always. We'll say almost always because there's always exceptions to pretty much everything. All right, so right now we're gonna go through and type these into Desmos. So let me go ahead and show you that. I'm just gonna start up Firefox and share that screen. But feel free to have your Desmos opened on another screen because you may want to follow along with me. Because there are certain things that we're going to do that's going to be different. All right. So everyone should see my Desmos window here. All right, we got to do a few things. You can't. I was like, you can't see it. It's right in front of you. No, you can't see it. Okay, good. All right. All right. So Google says press the mode button. Oh wait, I'm just reading past messages that I skipped over. Oh, you found a typo? Where? Well, let me know at the end so I can fix it. There's typos everywhere. Just got a new. Oh, you got a TI 30? Ooh. Ooh. Can you return it? Let me look up the TI 30. So which TI 30 do you have, Brady? There's a few TI 30s. Oh, the X2S. Oh, I really hate that one. I've used it before. That one, I believe, costs more. It does. It costs more than the Casio, and it does less. If you can return that TI 30 X2S, do it. Yeah, I hate that. Honestly, really hate that model. There's another model I hated more than that. That's a TI, but you didn't get that one. Uh, well, you can always just buy the Casio FX, and then once you get that, return the Casio. You have 30 days to return, assuming you have free returns or prime, or I don't know what the stipulation is. Yeah. So I sent an email about it. You should get the FX 115 or FX 300, and you can get the plus or the plus two, whatever version. I currently I have the first generation, but right now Amazon and I'm guessing Walmart, they sell the plus two, the second generation of it. Excited about math. Yeah. All right. All right. Brady, you good now? In the meantime, you can use it. You're just gonna have to Google on how to switch between degrees and radians because I don't have that model in front of me, even though I've used it quite a bit years ago. I don't remember. The FX 115S. I have to look that model up. All right. All right, everyone in Desmos, when dealing with these problems, we have to come over to this wrench, this little wrench button, the settings. Can all of you yeah, can all of you see my mouse when I'm moving it around? Okay. So we're going to hit this little wrench button here, and then we are going to do some things here. So the only thing that we need to do, well, we're in radians, so that's good. So this is important. We're in radians versus degrees. We should always be in radians unless, well, it's a different problem, but I don't think we ever switch to degrees. I don't think so, but I don't know. We'll see. Okay, what's really important on the x-axis? The step. You want to type in pi, pi, and then do divided by, and let's do 4. And then we can close the settings. And if you notice, my x-axis now has, well, it has the pi, and I got to zoom in a little bit, but, and now I have 0, pi over 2, pi, 3 pi over 2, 2 pi. Yeah, reverse contrast is kind of cool. All right, everyone good? Everyone's on the same step? All right, now we are going to type in one of our trig functions. Someone who has the guided notes open, what's the first trig function? Sine, cosine, or tangent? I forget. Okay, we'll do, yeah, sine. So we'll type in y equals the sine of x and then hit enter. And you can compare, you can look at your unit circle and also look at this to see how they're very related. And if you notice, sine, the parent function, sine of x. So whenever I say parent function, it's the function that doesn't have any type of translations or shifting. So yeah, so there's no shifting, there's no compression, expansion. It's the original function. That's a parent function. That's from last term. So sine of x. So we start at 0, and then it starts to go up, and then back down to -1, and then back to 0. So we said, what's considered a full rotation? How many radians? 2 pi. Now, do you notice that on this graph, we start here, we go up to 1, and then we go down to -1, and then we get back to 0. Do you see how we stop at 2 pi? This creates a full rotation. Now, you learned in geometry some vocab words like period. So can you remember what a period is in regards to trig functions? Like in your own words, what is a period? So Noah says a full up-down cycle. Jackson says a full cycle. Yeah, both are fine. So a period is the, in this case, the time. So I a lot of times I refer to the x-axis as time. So it's the time it takes to do a full rotation. So we start at 0, it goes up to 1, it goes back down. Now, don't be fooled. Just because we go to 0, we go to 1 and go back to 0. This is not a full rotation. This is a half a rotation. And you think about it, if you look at your printed unit circle that all of you should have in front of you, going to pi is only a half a rotation. We have to continue. So from here, it goes down to -1. So again, look at your unit circle. Our unit circle, like the coordinates, it's all the radius is 1 to correspond to this. So no matter where you are at the edge, so remember the center is 0, 0, the far right would be 1, 0, the very top of the unit circle would be 0, 1, the far left would be -1, 0, the very bottom will be 0, -1. So we get at 3 pi over 2, which is 270 degrees. We're straight down, and that's the coordinate is 0, -1. And that makes sense because there's your -1, the y value. Remember, you got to think about this: sine, cosine, tangent. Sine is what variable? This is from last week. Sine is what variable? Sine is the y variable. So like when I talk about, we look at the unit circle and we look at this, at 3 pi over 2, 270 degrees, we get -1 as your output. That is the y value. And on the unit circle, we can say, hey, sure enough, the y value is -1. Does everyone see that connection? Because it's important to understand that. You know, everything's like clicking together. It's all starting to make sense, I hope. And then we continue on for a full rotation. And if you look at the unit circle at 2 pi, y is 0. I'm looking back at the unit circle. At pi over 2, your y value equals 1 because that's 90 degrees. If you look at 0 degrees or 0 radians, the y value is 0. So remember, sine is the y value. And for this parent function, the period is from 0 to 2 pi. Period is 0 to 2 pi. Any questions on sine before we go to cosine? Nope. All right, now we're just going to type in cosine of x. So I'm going to unclick this so it hides it, go to this next line and type in y equals cosine x, hit enter. There's no need to put a space. When we type in cos x, it knows. It knows. How do they know? I don't know. Cosine x, and it puts that here. Now, we all know that cosine is what variable again? X. Yep. So at 0 degrees or 0 radians, we can see on the unit circle that the x value is 1 because the coordinate is 1 comma 0. If we keep rotating on the unit circle to 90 degrees or pi over 2, we can see that the coordinate is x equals 0. If we keep rotating to 180 degrees or pi radians, we can see the x value is -1. And if we continue and we finish the rotation, we get back to, we get to 270 degrees, which is 3 pi over 2, we can see that the x value is 0. The y value is -1. And then we finish our rotation. We get back to where we started at 2 pi. And we can see that the x value is 1. So another vocab word, 2 pi and 0 radians and 2 pi radians. What are those two called? So comparing both of them, what are they called to each other? Try not to give it away. Those are coterminal angles. Yes. Coterminal angles. 0 and 2 pi are coterminal angles. It's because if you look on the unit circle, they're in the same spot. Coterminal angles. The first 0 is no rotations. 2 pi is 1 rotation. I can go 4 pi, which is a second rotation, and so forth. So 0, 2 pi, 4 pi, 6 pi, 8 pi, and so forth. Those are all coterminal angles. So it should make sense that why 0 pi and 2 pi have the same x value. Well, it's because we're in the same spot. All right, everyone doing good so far? Okay, good. All right, and then lastly, we're going to type in the tangent. So I'm going to just unselect my cosine and type in y equals tan of x. Hit enter there. Kind of crazy looking. Oh, real quick, let me go back to. Sorry, I'm not done with cosine x. Can someone tell me what the period of cosine x is? Yeah, it's 2 pi. It's from 0 to 2 pi. A full rotation takes 2 pi time. We start here, goes down, and goes back up, 2 pi. All right. Now, tangent. Yeah, it's kind of weird. Kind of weird. Now, it kind of makes sense why this is doing this if you think about how these are working. But tell me, what is tangent equivalent to when talking about the unit circle? We said sine was the y value. We said cosine is the x value. What is tangent? Tangent is y divided by x. Yes. Yep. Now, what's different? So what's a characteristic about this graph that is not present in sine or cosine? So it's vertical, right? So Noah says there's spaces between. What are those spaces called? They're not holes, but no, you were very close. They're not holes. What's the math? We learned it last semester. So asymptotes. Very good. Yeah, those are vertical asymptotes. And can someone tell me what asymptotes are again? Yeah, it's just there's like these imaginary lines, in this case is vertical, where your graph will not touch or pass through. Those are asymptotes. They're sort of like holes, but they're not. A hole would be actually on the graph that has a discontinuity of the line. This doesn't have a discontinuity. This just has a vertical invisible barrier where it approaches but doesn't touch. So similar but different. Yeah, imaginary barrier. It's the force. The force is strong in those asymptotes. All right, now looking at this, can someone just, guys, really think about this? What is the period of tangent? So we want to do well, we want to do a full cycle. It is pi. Yeah, it is pi. And if you so from negative pi over 2 to pi over 2, that's a distance of just pi. So negative pi over 2 to pi over 2 is a distance of pi. So that is the period, and then it repeats from here to here, and then it repeats. So the period of tangent x is pi. I can try. So remember, period is the time it takes to do a full rotation, a full cycle. And by looking at the graph, the period is just pi. So right now, so this is one full rotation, and then it repeats. So it only takes a half a rotation to do a full cycle. But I should probably differentiate between saying full cycle versus full rotation because they are different. It's a full cycle, which is different than a full rotation would be 360 degrees. So to do a full cycle, you only need a half a rotation. For sine and cosine, you need a full rotation to complete a full cycle. So again, your tangent of x, you only need a half a rotation to complete a full cycle, and that's your period. Hopefully that helps explain. Sorry, I didn't make that clear earlier. Yeah, the period is making the full cycle. So basically, from when you start and when you go through the motions before it gets back to where you started and it repeats. That is the period before it repeats the same thing. All right. So let me go back to, oops. All right, there we go. And on the screen, I just have copy and paste to show what we just talked about. There's your sine that we talked about. So the The period is from 0 to 2 pi, or just 2 pi. For a full cycle, it takes 2 pi. Same thing for here. It takes 2 pi to complete a full cycle. For tangent, it only takes 1 pi to do a full cycle before it repeats. And then on this graph, I have the imaginary vertical asymptotes drawn in just to show them visually. That's a good guess. So it says, I'm guessing the period changes with stretches or compressions are applied to the parent function. You are totally correct. And you can probably guess we're going to get into that stuff later, just not today. Later this next week. I think next week. Not tomorrow, but next week. But yes, you are correct. All right, on this page, I talk about the domain, range, and the period. So this one, I kind of really focused on the period. Sine and cosine, to do a full cycle is 2 pi, and for tangent, a full cycle is just pi. So a half a rotation around the unit circle, or this is a full rotation on the unit circle. Domain and range. Can someone tell me in your own words what domain is? What is domain? Yeah, it's the x values or your input. Yeah, domain is your input or x values. And then what is range? Yeah, it's your output, your y values. Yeah, we should all know that by now. You know, that's something that should have been taught probably at the very latest your freshman year, but I think they teach it in grade school sometime. At least they should. All right, so domain. For sine and cosine, we can use anything for your input, and we can see that clearly on the graph. Oops. For every input, we have an output for sine and cosine, but looking at tangents, it's pretty clear. Remember VAs, vertical asymptotes, those are inputs that don't yield anything. It causes usually a divide by 0 error. Now, if you think about it, on the unit circle, if you look at the unit circle, we know that tangent is y divided by x. So looking at the unit circle, at what degrees, or yeah, so we'll say degrees, at what degrees does x equal 0? So everyone looking at your unit circle. So Noah says 90 and 270. So 90 is one of them, 270. Does everyone see that on the unit circle? And I want to say, let me see, I might actually have a unit circle somewhere on here. I do. Okay. I was smart and I put it on here. So everyone see that at 90 degrees, the x value is 0, and then at 270, the x value is 0. So does it make sense that we have asymptotes when you divide by 0, and that occurs at 90 degrees and at 270, or pi over 2 radians and 3 pi over 2 radians? Does that make sense of why you get asymptotes? Dividing by 0 is bad, right? It causes, like, I don't know, the end of the world or something. So that's why at tangent, you can use all inputs except at pi over 2, which is 90 degrees, and then they put it in a formula form. So they say pi over 2 and then plus pi times n. Or sorry, n times pi. N times pi. Ada, go away. N times pi. So on a unit circle, if I rotated pi every single time, how far are we rotating on the unit circle? (180 degrees). So if I said, all right, guys, we're going to rotate pi, that's a half a rotation. Does everyone see that? So that's why this is in this form here. They're saying the first place where, well, you get divide by 0 error because you can't divide by 0 because x is 0 at pi over 2. And then it's saying every time you do a half a rotation, n times pi, you also get asymptotes. So you start, so let me go to this next page here. So it's saying first one is here. Then they're saying, all right, we rotate a half a rotation. Hey, divide by 0. Rotate another half a rotation. Divide by 0 again. Rotate another half rotation. Divide by 0. So that's why this formula is written the way it is. Does everyone follow? Everyone's good? Is there a question? Trying to scroll. I didn't see a question. Did someone ask a question? I see a comment saying about me being busy or something. Okay. All right. I saw Isaiah's comment. Like I missed a question or something. Oh, you're talking about my cat Ada. Yeah. So I spell my cat Ada. Is how I spell my cat's name. Sorry. I was confused. Okay. All right. All right. So tangent, the main, so all the inputs is everything except 90 degrees, and every time you do a half a rotation. So 90, 270, and then another half a rotation. I don't know, math is hard sometimes. So that's what this is. And n can be an integer. So we can start at, so we can start at 0 because 0 is an integer. 1, 2, 3, 4, 5. We can also go negative, -1, -2, -3, and by plugging in that integer, negative or positive or even 0, we will end up either at the top of a unit circle or at the bottom of a unit circle, which would cause us to divide by 0, and that's why that's bad. Anyway, I think I really beat this one to death, so hopefully all of you are good. Now the range is your output. Easiest way is probably just to look at your the graph it creates. And it should be pretty clear to see that for sine and cosine, the highest value we get to is 1. The lowest value we get to is -1. So remember, that's your range. Your range is your output. So the highest is 1, the lowest is -1. And remember, range is in domain is always written least to greatest. So that's why they have from -1 to 1 brackets, because these are solid points, not hollow. Now, tangent, looking at the graph, it should make sense. It's all real numbers. Going back to here, look at this. Our graph goes up forever. It gets really close to the asymptote. It gets infinitely close as it climbs infinitely. This direction, it goes down forever and gets infinitely close to this asymptote as it approaches negative infinity. So your output for your tangent is all real numbers. Yeah. Any questions on this? All right. And I think that was the most difficult explanation of this lesson. There's the unit circle. And just to cover it again, these are the radians, those are the degrees. These are the coordinates with a radius of 1. So this circle has a radius of 1, if that wasn't clear to you. When I taught this course in person many, many years ago, I would teach this, and I would teach all of you how to memorize this. And for your test, I would give you a blank unit circle, and your job was to fill out this unit circle from memory and then use this unit circle on your exam. And you may say, hey, that sounds really difficult. It's really not, because there's patterns that I would teach. I'm not going to teach the patterns in here just because there's no way of me enforcing people not using it on your test. So you're welcome to use the unit circle during your quiz and during your exam. Yeah, if you couldn't produce the unit circle, you may as well just hand it in a blank test. All right, reciprocal functions. This is what they look like. I'm not going to type them in Desmos. Feel free to, but this is what cosecant looks like. This is what the secant looks like, and this is what the cotangent looks like. All right, so based on those graphs, just quickly go through it. Cosecant has a domain of everything except n times pi. So whenever you have a, basically whenever x is 0, and if you think about it, remember cosecant is the reciprocal of what? Sine. So cosecant is 1 over which variable? 1 over y. So it makes sense that we can't use anything where y is 0. And on the unit circle, y is 0 at 0 and at pi. So starting here and then doing half rotations. And that's why we have the domain being just that. So 0 times pi is 0 radians. 1 times pi is pi radians, and then so forth. So at those, thank you. Same thing for secants. We know that secant is 1 over x, so x can't be 0. And on the unit circle, x is 0 at 90 degrees and at 270 degrees, so that's why it has that domain. Cotangent, it's just, remember, reciprocal, so it's x over y, so y can't be 0. So that's why it has the same as secant, because it's x, because you're dividing by x, right? Hold on. Is that right? Got to think about this. Let me just write it down real quick so I don't. Thinking too much without writing is difficult. So we know that cotangent is x over y. So we cannot have y to be 0. And y is 0 at 0 degrees and at 180. So 0 and pi. So 0 and pi. This might be a typo. I believe this one should be the same as cosecant. Any of you want to agree with me on that? I would agree. And let's look at my graph. So at pi over, it is the same thing. I didn't see this part. Well, no, it's not the same thing. So they're saying, so when n is 0, we're at pi over 2. And looking at cotangent pi over 2, we have an answer. Yeah, it's wrong. I have a typo. Surprised I just noticed that. All right, so this should be the same as this one. I wonder how I messed that up. We'll probably copy and paste, and I don't know. Anyway. Yeah. Okay. We will, I'll fix that on my guided notes and I'll re-upload it. All right. And then the range, you can see these right from the graph. Cotangent is all the same. Cotangent is all real numbers, just like tangent looks very similar. And then the cosecant and secant, they're different. And based on the graph, you can see that the cosecant graph, it's out of the range. So it goes up forever and then it dips down to -1. So and then also on the other side, it goes down forever and then it goes up to -1. Hopefully I said that right. So negative infinity to -1, there's a gap, a union, there's a break, and then from 1 to infinity. Let me go back to this page. So yeah, so it's from negative infinity up to -1. There is a gap, and then it goes from 1 up to infinity forever. So that's your range. And the range for secant is also the same thing. All right, and the periods are going to be the same. Yeah, pulling out the domain and range should be relatively easy when you have the graph to look at. Like if I didn't have these graphs to look at for my range, and you just told me, hey, you asked me, hey, what's the range of these? I'd be like, I don't know actually. I had to graph it and look. I have no idea. All right, the last piece, odd or even. This is just looking at symmetry. We have, so it's even if f of x is the same thing as f of -x. And you can type this in, type in -x and then graph it, see if they're the same. One way to do it mathematically, I guess. Or you can just look at the graph, which I think is the easiest way, and just looking if it's symmetric about the y-axis. So remember, your y-axis is here. So take a moment and look at and see if you can figure out which ones are considered even. And look at all 6 graphs. Well, it's like we're all in agreement. I'm seeing people saying cosine is, people saying secant is. So does it look like this is symmetric about the y axis secant? I agree. Yes, this is even. And then people were saying, what was it? Cosine. So here's the reflection, right? The symmetry is this side symmetric to this side? Is it a reflection of itself? It sure is. So the answer to that would be cosine and secant. And that's considered to be even. And we could type -x into it. So, I haven't done this. Let me actually make sure it works. What if it didn't? So we said cosine x, and then we said all right. Yeah, let me share my screen with you real quick. All right. So we have cosine, and then to be considered even, it has to match f of negative x. So in other words, it wants us to plug in negative x wherever we have x. And if I plug that in and I turn this on, look, it's right on top. Turn this one off. Right on top. So that's another way you can check graphically. All right, and then the odd ones. So this one is, it's a little different. Again, mathematically, you could type in, we can check to see if f of negative x is equal to the negative of f of x. So we would compare these graphically to see if they are the same. And if they are, it would be considered odd. Or you can just look at the symmetry about the origin. So about the origin. So looking at these graphs again. So this is the origin. This is the origin. So we already know this one's even. So that's not even an option now. So looking at all 6 trig functions, which ones are considered odd symmetry? I'm going to give you a hint. Actually, I'm not, because then I give it away. No hint. So cosecant, sine. Rachel says the rest of them. And some of you are partially correct. Some of you are all the way correct. So the answer is all the rest of them. Yeah, all of them. Or not all, but the remaining 4. Yeah. and Enzo's logic is sound. If they're not even, they're odd. It's one or the other. There you go. Fair enough. Yeah, if they're not even, they're odd. I think that's good. Yeah. So we know, if we know these are even, the rest of them are odd. Yeah. All right, and that is it. Please take time to mess with Desmos if you haven't already, to type stuff in to make sure that you know how to set the x-axis to radians. Well, it's already in radians, but to put the labels of doing like pi over 4 or pi over 2 or whatever you want to do. I think I usually do pi over 4 because pi over 2 just puts, wait, pi over 2 doesn't put enough. Yeah, we need pi over 4. I think. Anyway. Well, guys, as always, thanks for coming. I hope you learned something. I will see all of you tomorrow for day 2 of 3.02. So exciting. So exciting. All right, guys. Have a good rest of your Thursday.